Sometimes I feel like the stuff you send our way, it's like, whoa, it just throws open a whole new door in my brain.
Right.
We're always talking about the universe on this huge scale, right? Galaxies, black holes, the whole shebang.
Right.
But then you remind me that some of the biggest puzzles are actually hidden in the tiniest things. Like these neutrinos, they're everywhere. I mean, trillions of them are passing through us right now, every second.
Yeah.
But the fact that they even have mass, and it's such a tiny amount, it's mind-boggling. So that's what we're diving into today, thanks to this research you sent.
Yeah, it's really cool because for the longest time, the standard model, it basically said neutrinos were massless.
Right.
It was a big deal when we found out they actually do have mass, even if it's super tiny.
So it's a big deal.
Huge. And now we're trying to figure out how they get this mass and why it's so much smaller than other particles. I mean, it's weirdly small. It's telling us there's something else going on, something beyond what we currently understand.
Okay, so your sources bring up this wild idea, TV-scale gravity models. Now, I'll be honest, I'm not a quantum gravity expert or anything. So
Right.
for those of us who, aren't wrestling with that stuff every day, what are we even talking about here? And how does this connect to neutrino mass, which seems like a totally different thing?
Well, basically, TV-scale gravity models, they suggest that gravity, the force we all know, might actually become strong at much lower energies than we used to think. Way lower than the Planck scale, which is this crazy high energy level.
Okay.
And if that's true, it means we could actually see quantum gravity effects, in our experiments.
Yeah.
Which would be amazing.
Wow.
And one of the coolest things that could happen is we could create tiny black holes.
Wait, hold on. Black holes, mini black holes just popping into existence.
Yeah, exactly.
That sounds like straight out of a sci-fi movie. But you're saying these tiny black holes could help us understand why neutrinos have such a small mass.
Exactly. The research you found, it proposes this totally new mechanism. It basically says these TV-scale black holes, they can kind of break some of the rules of physics that we're used to.
Okay.
And this rule breaking, it could be the reason why neutrinos have this incredibly tiny mass. What's really cool is that this one idea, it connects things happening at completely different scales.
Yeah.
From the subatomic world all the way up to, these crazy high energy events in space.
It's like a unifying theory.
It is.
Yeah.
That's what physicists are always looking for.
That's amazing.
Yeah.
So for this deep dive, we're basically going into this crazy world where the smallest things might be connected to black holes, which are some of the most extreme objects out there.
Right.
We're going to see how these TV-scale black holes could give neutrinos their mass. And we'll also look at how this idea actually fits with other things we see in the universe, which is pretty cool.
Exactly. We'll go through it step by step. We'll talk about how it explains the neutrino mass, but also how it connects to other weird stuff, like neutrinoless double beta decay. It's this process that could totally change how we understand matter.
Wow.
And even ultra-high energy cosmic rays. Those are the particles with the most energy we've ever seen.
Okay, so let's start with the basics. We know neutrinos have mass. Why is that a problem for our current theories? And what's all this about Majorana mass and lepton number violation? I keep seeing those terms in the research you sent.
So the thing is, the standard model is our best theory for how particles work. But it doesn't really explain how neutrinos can have mass.
Okay.
It doesn't fit in neatly. The fact they do have mass, it's a sign that there's something more going on. Now, your sources talk about this idea that neutrinos could be Majorana particles. Imagine a coin with heads on both sides.
Okay.
It's kind of like a Majorana particle. It's its own antiparticle.
Uh-huh.
And if that's true, it means they can have this special kind of mass called a Majorana mass. But to have that, you got to break this rule called lepton number.
Lepton number, is that like a cosmic rule book or something?
Like a cosmic accountant. He keeps track of these particles called leptons, like electrons and neutrinos.
Right.
And it makes sure the number of leptons minus the number of antileptons stays the same. But if you violate that rule, whoa, that's a big deal. It messes with how we understand how particles interact.
So it could explain why there's more matter than antimatter.
Yeah, exactly. It's a big mystery.
Okay, so if neutrinos are Majorana particles, their mass is basically a sign that we're breaking this lepton number rule. Now, how do these TV-scale black holes fit into this? How are they breaking the rule?
Well, the idea is that black holes, they're so extreme, they can basically ignore certain symmetries. Symmetries are like these fundamental rules in physics that say things should stay the same even if you change them in some way.
Yeah, like flipping something over and it still looks the same.
Exactly. But there are different types of symmetries. Some are associated with the forces we know, like electromagnetism. Those are tough to break.
Right.
But lepton number, it's not one of those. It's more delicate. And black holes, with their crazy gravity, they can just, ignore it. So they can create or destroy leptons without their anti-partners, which breaks the lepton number rule.
So they're like the rebels of the universe, breaking the rules that everyone else has to follow.
Kinda, yeah.
I like it.
And it's this rule breaking that could be behind the whole neutrino mass thing.
Okay, I'm following. Now let's get into the details of this black hole neutrino mass mechanism. Like, how does it actually work? Walk me through it.
All right, so imagine our universe, but with more dimensions than we can see, like hidden dimensions curled up really small.
Okay, I'm imagining.
Now, in these TV scale gravity models, these extra dimensions, they can kind of fluctuate. And sometimes these fluctuations, they can get so intense that they create a tiny black hole.
A black hole from a dimensional ripple.
Yeah, it's pretty wild. And the mass of this black hole, it's important. It has to be around 5 times this fundamental energy scale. We call it MD. Now, this MD, it's not the same as the Planck scale, which is like super high energy. It's much lower, maybe in the TeV range.
Okay.
And that's important because it makes these mini black holes possible, at least in theory.
Okay, so we have this tiny black hole, 5 times MD. What happens next?
The key part is that this black hole, it doesn't care about lepton number. It can decay by emitting 2 neutrinos.
Okay.
Now, here's where the Majorana part comes in. If neutrinos are their own antiparticles, then this whole process, the black hole appearing and decaying into 2 neutrinos, it looks like a neutrino is just traveling along, but it has this tiny black hole insertion for a split second.
Wait, so it's like the neutrino takes a detour through a black hole?
Yeah, kinda. And because we're assuming it's a Majorana neutrino, it's like it's interacting with itself through this black hole. That's what gives it the Majorana mass. It's like a little boost of Majorana-ness from the black hole.
Okay, that's starting to make sense.
There's actually a diagram in the source, figure 2, that shows this. It's like a neutrino goes in, there's a black hole in the middle, and a neutrino comes out. That interaction in the middle, that's where the Majorana mass comes from.
Cool. So this fleeting black hole interaction gives the neutrino its mass. But what about the energy involved? And the other particles, the Higgs bosons? The source mentions some constraints on the black hole's mass and how many particles it emits.
Right, so for our calculations to work, the black hole's mass, we call it MBH. It needs to be at least 5 times MD.
Why 5 times?
It's kind of like a sweet spot.
Yeah.
If it's smaller, our calculations might not be accurate. But if it's bigger, it's way less likely to form in the first place. So 5 times MD, that's where things get interesting. Now, if you look at figure 1, it shows that a black hole this size will usually emit about 4 particles when it decays.
4 particles?
Yeah, and the specific decay we're interested in, the one that gives neutrinos mass, is where it decays into 2 neutrinos and 2 Higgs bosons. But there's a catch. The probability of that happening, it's super tiny, like 9.3 times 10 to the minus 9. It's way more likely to decay into other particles.
So it's like winning the lottery, but with even worse odds.
Pretty much.
Wow. Okay, so we have this super rare event, this tiny black hole popping up and decaying in just the right way. How does that translate into the actual mass of a neutrino, which is, ridiculously small?
Well, there are a bunch of factors that make the final neutrino mass so tiny. Like it's a whole chain of suppressions.
Suppressions.
Yeah, like things that make it smaller and smaller.
Okay.
First, a black hole itself, it doesn't stick around for long. It exists for a super short time. And that gives us a suppression factor of like 1 over 15.
So it's already 15 times smaller just because of how short-lived the black hole is.
Exactly. Then, for the black hole to even decay, the energy has to be trapped inside its event horizon, the point of no return.
Yeah.
That adds another suppression factor, something like 1 over 5 cubed.
Cubed, so 1 over 125.
Yep, exactly. Then we have the tiny probability of it decaying into the 2 neutrinos and 2 Higgs bosons. That's the 9.3 times 10 to the minus 9 we talked about. And finally, the Higgs bosons themselves, they interact with the vacuum and get a vacuum expectation value, or VEV.
Okay.
But this VEV, it's much smaller than the fundamental scale MD. So that adds another suppression factor, something like 0.174 TeV over MD, all squared.
Whoa. Okay, so it's like a whole cascade of things making the mass smaller and smaller.
Yeah, it's like a cosmic game of telephone where the message gets quieter and quieter each time it's passed on.
I love that analogy. So when you put it all together, all these tiny probabilities and suppression factors, what's the final prediction for the neutrino's Majorana mass?
When you crunch all the numbers, you get this really neat formula. It's M equals 0.7, 5 EV times 1 TeV over MD. And remember, MD, we think it's in the TeV range, so thousands of G. So this formula, it automatically gives us a tiny neutrino mass in the electron volt range, which is exactly what we see in experiments. It's a really elegant way to explain why neutrinos are so much lighter than all the other particles.
Wow, that's really cool. So just by thinking about these tiny black holes, we can get a neutrino mass that matches what we actually observe. Now, the research also talks about neutrinoless double beta decay. What is that, and how does it connect to all this?
So neutrinoless double beta decay, it's this hypothetical radioactive decay. It's where a nucleus emits 2 electrons, but no antineutrinos.
No antineutrinos.
Yeah, which is weird because in normal beta decay, you always get an antineutrino. But if neutrinos are majorana particles and lepton number is being violated, like we've been talking about, then this neutrinoless decay becomes possible.
Okay, so it's another sign that lepton number might not be such a strict rule after all.
Exactly. And there's actually an experiment, the Heidelberg-Moscow experiment, that might have seen evidence for this decay. They suggest a range for the neutrino mass, with the best fit being around 0.39 eV.
So they're seeing a neutrino mass that's in the same ballpark as what we get from the black hole mechanism.
Yeah, which is really interesting. And there's a diagram in the source, figure 3, that shows how a black hole could make this decay happen. It's like 2 neutrons in a nucleus, and a black hole pops up between them, mediating this exchange of a Majorana neutrino. Since the neutrino is its own antiparticle, it allows the neutrons to turn into protons and emit 2 electrons, but no antineutrinos.
Okay, so the black hole is like a facilitator making this weird decay possible.
Exactly. And the Majorana mass we calculated, it's directly related to the mass that experiments like Heidelberg-Moscow are trying to measure. By matching the two, we can actually figure out limits on the fundamental scale MD.
So we can use the experimental data to narrow down the possible values for MD.
Yeah, and what they found is that MD should be somewhere between 2.7 TD and 14 TV, with the best fit being around 3.8 TV. In that range, it actually makes sense in TV scale gravity models. It's not some crazy number that doesn't fit with anything else. It's actually pretty natural.
So it's all starting to come together.
It is.
But what about the bigger picture? Does this black hole neutrino mass idea work when we look at things like dark matter and cosmic rays?
Yeah, it actually does.
Yeah.
First, let's talk about dark matter. Neutrinos, they're so light that they're considered hot dark matter. It means they're zipping around really fast.
Okay.
And if they were much heavier, it would mess up how galaxies and galaxy clusters formed. Luckily, the Majorana mass we got from the black hole mechanism, it's small enough that it doesn't cause any problems. It fits with what we know about dark matter.
That's a relief.
Yeah. It also means that neutrinos only contribute a small amount to the total matter in the universe, like less than 13%, which is also what we expect.
So no conflict with dark matter. What about cosmic rays?
All right, so cosmic rays, they're these super energetic particles coming from space. But there's a limit to how energetic they can be, called the GZK cutoff.
The GZK cutoff?
Yeah, basically, if they're too energetic, they should interact with the stuff in space and lose energy. But we see cosmic rays that are more energetic than that.
So something's not adding up.
Right. And one explanation is this thing called the Z-burst scenario. It's where super high-energy neutrinos crash into other neutrinos left over from the Big Bang.
Okay.
And this creates these Z-bosons, which then decay into other particles that we see as cosmic rays. But for this to work, the neutrinos need to have a certain mass, somewhere between 0.08 eV and 1.3 eV.
And does our black hole neutrino mass fit into that range?
It does for most of it.
Yep.
It actually gives us another limit on MD, saying
Ah.
it should be between 0.58 TV and 9.4 TV. There's a slight hiccup with the lower limit, but overall, it's pretty consistent with everything else we've seen.
Okay, so let me get this straight. We've looked at neutrino mass, this neutrinoless double beta decay, and ultra-high energy cosmic rays. And this black hole idea seems to tie them all together. It's like a single thread connecting all these different parts of the universe.
It is. And when you combine all the limits on MD from all these different areas, you get a range of 2.7 TV to 9.4 TV.
That's amazing.
It's a pretty strong indication that this mechanism might be the real deal.
And the coolest part is we might actually be able to create these tiny black holes in the LHC.
I know, right? If we see them and we measure MD and it matches what we get from neutrinoless double beta decay, that would be incredible. It would be like proof that this whole black hole thing is really happening.
But that would be huge.
It would be revolutionary.
So, to sum it all up, what we've learned today is that the tiny mass of neutrinos, this weird decay process, and even these crazy cosmic rays, they might all be connected through these tiny black holes.
Exactly. It shows how things that seem totally different can actually be deeply connected.
It really makes you think. Like, if these black holes are really out there, what other mysteries are they involved in? What else don't we know? It's mind-blowing.
I know, it's like the universe is even more interconnected than we thought.
And that's what makes this so exciting. There's so much more to discover, so thanks for sending us down this rabbit hole.
Of course. It's been a wild ride.
And to all you listeners out there, keep exploring, keep asking questions. Who knows what other mind-blowing connections are out there just waiting to be found.